Hi, Charles. So nice to have you again. Welcome to another session. Today we're going to be going through physics. We're going to be going through work, energy, and power. So I hope you guys have readied your brains to kind of go through this topic. So this one isn't too bad, especially considering that a lot of the formulas that you use in work, energy, and power you are given in your formula sheet. And so I don't think you guys, it can be a little bit tricky, but it's very doable if you know how to approach certain questions. So there is a chat, and I'll be able to see the chat. So how we're going to run today's one is that if you find that you're really struggling with to understand something, let me know as soon as you find whatever you're struggling with, and then we'll try and tackle it then. I'm just trying to see why my device won't scroll up. It's acting a bit. There we go. Okay, I'm sure I'll fix it. But there is a chat that I'll be able to see. You can ask your questions there. And if there's something that you're really, really confused about and you're just like, ah, ma'am, you lost me, I'll be able to see that chat, and then um, you, I'll try and address every single question. If I do miss anything, you can ask again, and then I will be, I'll be sure to make sure that I address any very burning questions. But just make sure that when you do ask a question, you specify what exactly you are struggling with. So don't just say, I'm confused, or I'm lost, or I don't understand what this and this is. Try to be as specific. So say, I don't understand what we did in question 3.1, or I don't understand the definition of work. Can you please go through that again? Then I'll know exactly what to go through, and we won't be wasting time waiting to hear what exactly you are confused about. Okay, so you guys can let me know if I'm moving too quickly, too slowly, if you want me to speed up, whatever it is, I'll be able to see it in the chat. Okay, cool. So today we are starting with work, energy, and power. And I love this topic because, again, it's quite simple if you know how to apply each and every one of the formulas. And so we're going to look at every single formula that you need to know. And if there is any specific tips and tricks that you can use to kind of tackle each and every one of your questions, then we will make sure to go through that. I just want to see that the chat is working. Can you guys send me like, hey, we're ready in the chat, just so I can see that the messages are coming through to me. There we go. Okay. Okay, cool. Perfect. I can see. There we go. Okay, cool. So work, energy, and power. So work, energy, and power is something that's focused more on, or like they use a lot of assumed knowledge. They assume that you're familiar with Newton's laws. They assume that you're familiar with some of the grade 11 concepts that go around like finding the resultant forces or knowing what forces are on a specific object. So let's say there's a car going down a hill, like what forces are on that object. And that's something that you need to be able to know. So we won't go through it today, but just make sure that you are familiar. We'll go through some questions and I'll work you through it if it is a bit confusing. But you need to do some background. Like you have to have some background knowledge on how to work through a free body diagram. Like how do you draw the forces on a certain diagram or on a certain object? And from there, you can then calculate work, and you can use work energy theory to find certain things, and you can also find the power that is applied to a certain system. Okay, so the first thing is, what is work, right? And so work is essentially energy that's transferred from one system to another, or one object to another. So when we think about how we know that there's a law that says energy cannot be created or destroyed, but only transferred. We can say, okay, cool. If we're transferring energy, what does that look like? What does that mean? So if I have, I think I have a nice diagram here. If I have somebody pushing on a bookshelf or pushing on a wall, right? If they're strong enough, and this is just a small little bookshelf that they can push, they are able to, they would be able to push this book, and therefore transferring the energy that they have in terms of a force, and converting it or transferring it to the bookshelf and turning it into kinetic energy. And so that's basically what work is. We look at how energy is transformed or transferred from one system to another. And so here we have our basic equation for work. And so this W obviously stands for work, right? Because it's W and W. And this force is the force applied, right? So this is either force applied, this can be gravity, this can be friction. So we are looking at any force that acts on an object. This can be normal force. So any force that acts on an object has the potential to do work under certain conditions. We then have our delta x, which is the displacement. So this is the displacement, sorry. Displacement. And this is how far an object has moved from its place of origin. So if it starts here at x equals 0, how far has it moved to get to its final destination? And then we also have this cos theta term. Now we'll look more into that and what that means. But this is basically how the force is going to be applied in a certain direction, and we want to see, is it moving in the same direction as this force is being applied? Is it moving in the opposite direction to which a force is applied? And so we can look at work in different ways depending on what direction the force is being applied versus what direction it's actually moving in. Okay, so just to sum it all up, work is basically, when we're looking at work, we're looking at how energy is transferred from one system or one object to another, right? And so we need certain requirements for work. So we said there's so many things that can act on a system and do work on a system, right? And so for work to be done, we firstly have to have a force acting on an object. We cannot, if we don't have a force, we cannot do work on an object, right? So if I don't apply a force, or there's no gravity, or there's no normal force, or there's no friction, we cannot do work on that system or that object. We also need a displacement, right? So it needs to move. If it doesn't move, then no work is done. So like we have here, if I have a man pushing on a wall and he's pushing as hard as he can, if that wall does not move, then no work is done on that wall, right? So we need these two key things. We need a force and we need a displacement. We need to apply a force or have a force acting on that object, and we need it to move by even just by like a little fraction. It needs to move or else no work is done. Okay. And so now we look at this case. So before we looked at a man pushing on a wall, and we said that doesn't do any work because there's no displacement that's acting on that. But if I have a man pushing someone else on a chair, right, we have a force that's being applied. And if this chair moves from this initial position to this final position, then we can say that work has been done on the chair and on the man that's on the chair, right? And so we would look at the force, we would look at the distance that the force has traveled or the object has traveled, as well as the angle, which we'll look at just now in a few slides. Okay, does that make sense? Is everybody okay? So we need force and we need a displacement in order to do work. Okay, perfect. So, like I said, we have different types of work, right? You get positive work, you get no work, and you get negative work. Okay, so I'm going to draw a diagram here on the side. So if I have, let's say, a block, right? And on this block, I apply a force in this direction, right? So this is me pushing the block, right? And this results in this block moving from where it was there to there, right? So this displacement, delta x, right? It's moved to the right. So in this case, my force was to the right, and my displacement, so where it ended up compared to where it started, this was the initial, this was the final, displacement is also to the right. So we get positive work. Now, the way that this is described mathematically is we can look at our equation for work. So we said work is equals to force multiplied by my displacement multiplied by my cos theta. Okay. When we look at the direction of, so we look at this theta in terms of the direction of my force versus my displacement, right? So when I look at my force is going in that direction, right? So we said this is my force. Then my displacement, I'm just going to draw it in, let's draw it in black, is also acting in that direction, right? That's the direction that my displacement is working in. Can you guys see that there is no angle between my force and my displacement, right? Yes, we do. We have theta equal to 0. And so if we had something different, like my force being in this direction and then my displacement is being in this direction, this over here would have been theta. So we would have a difference in, so let's say I'm pushing it this way, but it's actually going up a slope or something like that. That means that we have an angle between the direction in which my force is being applied versus the direction in which it's moving, right? And so we say positive work is done whenever theta, so that the distance between the force, or the angle between the force and the displacement, so the angle between the force and the direction in which it's moving, is less than 90 degrees. So if I have my theta being less than 90 degrees, then I get a displacement, I get a positive work done. Now, what does that mean for us? Can you guys put in cos of, okay, let's look at this first term, this one over here. Cos of 0. What is cos of 0 degrees? What does cos of 0 give you? Yes, cos of 0 gives you 1, which means that when the force and the displacement are acting in the same direction, that means that my work equation just turns into force times displacement, because then cos of 0 is just 1, and so you get a positive value for my work. You're always going to put your force as a positive. You're never going to put a negative force in this case, right? So you'll never put a negative force, and you'll never put a negative displacement when you're working with work, energy, and power. You're always just going to use positive values, and this cos is going to be the one that determines whether you get a positive work or a negative work. So these must always be positive when you're working with work energy. Even if it was working the opposite direction to which it was moving, you always write your force and your displacement as positives. Okay. Now, we also get negative work, right? So can somebody tell me what you think, or what force, or what kind of force could give you negative work? So I don't need why, but just what force do you think could give you negative work? Friction, right? And so how negative work works is, let's say I have a block, right? And there's a certain force being applied to it. I really don't mind what the force is at the moment. And that force is causing it to move in this direction. So my delta X is towards the right, right? We know, let's say this is going to be on a rough surface, so it's not a smooth surface. So we have friction acting on it. Friction. We know that friction always acts in the direction opposing motion. So if my object is moving towards the right, friction is going to move towards the left. So the force of friction is going to be opposite the direction in which I am moving, or the block is moving, right? And so now, can you see that my displacement is in this direction, but my force is in this direction when we're talking about the force of friction? Right. And we have done angles on a straight line before. What is this equal to? What angle is this? 180 degrees. Perfect. Right. Now, what does cos of 180 give you? It gives you -1, which means that if I have, let's say now I'm looking at the work done by my friction, that is going to be the force of friction multiplied by the distance that it moves, multiplied by cos of 180. Now we said cos of 180 is -1, which means this is going to result in a negative force. So it's going to be negative the force of friction multiplied by delta X. So this will give you negative work. And so this is where you would get negative work. The other one was positive work because it was moving in the same direction as the block was moving. So the force was in the same direction that the block was moving. But in this case, the block is moving to the right, but my force is being applied to the left. And so we get negative work. So this frictional force is always going to be positive, even if it's in the opposite direction of motion. So that's going to be, you're going to put a positive value in here and a positive value in here, but overall, you'll get a value that is negative. Okay. Then you also get instances where no work is done, right? So no work. And so what is an instance, or what force does no work on an object? Can you guys think of an example? Perfect. Well done. Yes, gravity and normal force. Both of those do no work in certain circumstances, right? So let's say, again, I have my block and it's being moved by something. I don't care what it's being moved by, but I know that it's moving in this direction. So my delta X is in this direction. We know that normal force or gravity, both of them, normal force always acts perpendicular to the surface, right? And so it will always act up. So normal force is there. We also have gravity working down there, right? This is just a normal block on a straight line, right? So let's say I want to now calculate the work done by the normal force. I would say, okay, work done by the normal force is my force, normal, multiplied by my delta X, multiplied by my cos of theta. Now we say that, okay, this is my delta X and my normal force is acting upwards, right? So the angle between these is 90 degrees. What is cos of 90 degrees? 0, right? So if I substitute in my cos of 90 degrees, I'm going to get force done by work multiplied by delta X multiplied by 0. And anything multiplied by 0 is 0, which means that this is doing no work for my system, none whatsoever. It's not transferring energy from any form to another. It's just a force that's present that's not contributing to any of the energy transfer from one form to another. Okay. So this is the case where we have normal force. So whenever you have a force acting in a perpendicular direction to where the the object is moving, you always have no work being done. Okay, does that make sense to everyone? Okay, perfect. Okay, remember, if you have any questions, you're welcome to put them in the chat and then I'll be able to answer them. So we looked at a case where we have no work because the force is perpendicular to direction in which it's moving. We also looked at negative work where the force of friction is in the opposite direction to the direction in which the object is moving. And we also looked at positive work where the direction of movement is the same as the force applied. So that they're moving in the same direction or they're pointing in the same direction. Okay. And so this is just what these blocks were showing. Okay. So I have this question over here. It says, I push a block of 3 kilograms with an applied force of 10 newtons to the right. A frictional force of 2 newtons acts on the block, right? Here, we want to calculate the work done by the applied force. So we're just looking for the work done by the applied force. The first thing you're always going to do is draw a free body diagram. This is a nice, simple problem. So the free body diagram isn't going to be too complicated, but you're always going to want to draw it so that you can fully analyze what forces are acting on your system. So in this case, it looks like, oh no, it won't draw a straight line for me. So in this case, it looks like a block, right? It's being pushed, it's 3 kilograms. It's being pushed with an applied force of 10 newtons. So F applied is 10 newtons, or you could have it being, no, it's being pushed, so it has to come from the side, and a frictional force of 2 newtons, right? So we have friction, which is acting in the opposite direction to which the block is naturally going to move. So frictional force is equals to 2 newtons. And then we have, what other forces do we have on here? I think I'm missing some forces. What forces am I missing here? I'm missing the force applied by gravity. So the force acting downwards, which is just going to be mass times 9.8. And I'm also missing my normal force, right? So the force that acts from the surface, and that's also going to be equal to mass times 9.8 in this case because it's on a flat surface. Okay, so these are all my forces acting on my block. Perfect. Now I said I want to find the work done by just the applied force. So I'm going to say work done by the applied force is going to be the force applied multiplied by delta x multiplied by cos of theta. Right. Now, my force applied, they told me that it is 10 newtons. So now I can put 10 multiplied by delta x. A push, let's say it moves 5 meters. They didn't tell us here, but I'm going to say 5 meters, 5, and then cos of multiplied by cos of theta. What is my theta? When I'm looking at my applied force, I have my applied force being acting in that direction, and my x is also acting in that direction. So my theta is going to be 0. Perfect. Well done, guys. So here I have 10 times 5 times 1, which is going to give me 50 joules. So work is measured in joules. Okay, so my work done by the applied force is going to be 50 joules. Okay, does that make sense to everyone? We're good with that. That should be nice and simple. Yes, I did make up the displacement. My question didn't come with one, so I just said my displacement is delta, is 5 meters. So work is energy transferred. So the energy that moves from one system to another. That's what work would be classified as. It's not energy, but it's energy that is transferred. Yes, so it's kind of like energy. Yes. So here we were just looking for the work done by the applied force, not the net work. So Nathan, if we wanted to find the net work, then we would have said minus the force of friction at work. Okay. Skylar, I'm not too sure what you're asking, but this one should be nice and simple because it's straightforward. We don't have any like weird complications. Okay. Now, then I say, I push a 3 kilogram block, so it's the same thing. I still have my diagram. It moves from there to there. This is 5 meters. And I have a force of 10 newtons that's being applied. My frictional force is still 2 newtons this way. And I still have my normal force, and I have my weight here. Okay. You can kind of, what would you be calculating with your equations of motions? You can kind of, to find the force. If you're asked for the force and you have like acceleration and stuff like that, then you can, but that comes a little bit later when you're starting to work with the work energy theorem. So we will get to that where you use kind of the equations of motion to find what certain values are. Okay, but here they're saying, what is the work done by the weight? Now, what is the weight equal to? Let's try and make this a small w so that we don't get confused. Weight is equals to mass times gravity, right? The mass here is 3 kilograms. Gravity is 9.8. So my weight is going to be 3 times 9.8, which is going to be 29.4 newtons. Okay, so now I know what force or the force that weight has, and so I can say that the work done by weight is going to be the force of weight multiplied by the displacement multiplied by cos of theta. Okay, so now we have the force of weight. We said 29.4 multiplied the displacement. Again, it moves. This is always going to be your displacement, so the direction that it moved is going to be 5 multiplied by cos. What is my theta? My theta is going to be 90 degrees because I have my displacement is delta x and my weight is acting downwards. So this is a 90-degree angle between them. So I'm going to have cos of 90 degrees here. And we said cos of 90 is equals to 0, right? And so that means that we're actually going to have this whole thing turn to 0 because it's going to be 29 multiplied by 5 multiplied by 0. So my work done by the weight is 0 joules. Okay. Okay. I hope that makes sense. That shouldn't be too bad. Again, the only tricky part would be finding out what your theta is. And so we know that if my displacement is towards the right and my weight is acting downwards, then the angle between my displacement and my weight is 90. And that makes cos theta equal 0, which means that we have 0 joules as our work done by the weight. Okay. Now they said, what is the work done by the frictional force? Again, we're still using our diagram, which has 10 newtons here, 2 newtons here, I want you guys to try this one. We have our force of normal and we have our weight here. What is the work done by frictional force? So we're finding the work done by friction. What is that going to equal to? And we also have our displacement again is still from there to there is 5 meters. So we can't use 270 as theta in this case because the angle between my weight and my displacement is 90. And oh, you actually, wait. What is cos of 270? Is it 270? Yes, cos of 270 is still 0. So if you find cos of 270, so you could have looked at it as this angle here, right, which is 270 degrees. That'll still give you 0 as your joules. That's a very good question. Yeah, so you could use both of either one of them and you'll get the same answer. Okay, I see people are getting the answer right, which is perfect. Well done, guys. So we know that my frictional force is always going to be positive, so I'm going to put it as 2 multiplied by my displacement, which is 5. Dx always faces the way that the object goes, yes. So my displacement is always going to face the direction that my object goes. And so, and then I multiply this by, so I have my displacement in this direction, and then I have my frictional force in this direction. And the angle between these two is 180 degrees. I'm going to have cos of 180 degrees, and this is equal to -1, right? So now I'll have 2 times 5 times -1, oh, -1, sorry. -1, this gives me -10 joules. Okay, so just make sure that you incorporate and you include that -10 joules over there. Okay. So why are they including a distractor? Because I was confused by the force applied. So they're just including it just so you can have it there. Sometimes they'll give you things that you don't actually need, but oftentimes they will give you things that you need. But in this case, they wanted you to work out the force one by one. So here they gave you the force applied, but you didn't actually need it. They just wanted the work done by the frictional force. So if they want the work done by specific force, you only consider that work. You don't look at how other ones affect it or how other ones move it in a certain direction. You only look at the force that they're asking you to look at. We will get to a net force, a network kind of question. We have to look at all the different forces that are acting on it to find maybe the net force, or just like look at the different work equations for each of them and then find the network. But if they ask you specifically just for frictional force, you're only going to look at frictional force. So if the examiner doesn't give you displacement, they'll give you some information that will help you get to displacement. So you can never calculate work if you don't have the force and the displacement. You always need to have both of those to be able to find what your work is. Okay. So whatever you put in your force is always going to be positive, no matter what it is. So you'll never substitute in, so when you're calculating work, force, delta x, cos of theta, these two, you're always going to put them in as positive values. You're never going to put them in as negative values, no matter what direction they're working in. Okay, and then I see you can't say, Garabo, you can't say that work is acting to the left. Someone is saying here, they're correct. Work is not a vector, so it can't have a direction. It can only have a quantity. So we say work is a scalar. So it only has it can have a negative or a positive, but it can't have a direction. Yes, work is a scalar. Is that how you spell scalar? It's an O. No, that's an A actually. Okay, cool. Now we have network, right? And this is like we've looked at now where we have one force acting on the object, two forces acting on an object. There's so many different forces that can be acting on an object. What happens when they're all working together? Can I find the network acting on an object? Okay. So I have now a box, a 3 kilogram box pushed for 2 meters across a rough surface with an applied force of 5 newtons. So it's pushed 2 meters across a rough surface, which means we'll have friction, with an applied force of 5 newtons and experiences a frictional force of 1 newton. Calculate the network on the block. Now there's 2 ways that you could do this. So I'm going to show you both of the ways. So let's just draw our free body diagram. They said that, so there's 2 ways. I'm going to start the 2 ways. All right. I'll have the same free body diagram here. It is moving on a rough surface. It has an applied force of 5 newtons and a frictional force. So this is F applied. And then we have a frictional force here of 1 newton. The other forces acting on this thing are the normal force and the weight. Right. Oh, let's make this a small w. That's the weight. Yeah, that's about it. They want the network on the object. So the first way that you do it, so way 1, is by finding the work done by each force. So work net is going to be equal to work done by the applied force plus work done by the frictional force plus work done by the normal force plus work done by the weight. Right. So this way we look at all the different forces. Okay. So what is the work done by the force applied? That'll be, we know that, okay, the major equation is going to be force delta x cos of theta, right? So the work done by the applied force, we can see that the applied force acts in that direction. Oh, sorry, and then this has moved 2 meters equals delta x. We know that this is where delta x is moving in, and we can also see that my force applied is also acting in that direction. So my angle is going to be theta. Oh, my theta is going to be 0. So I'm going to say force applied is 5 multiplied by the displacement, which is 2 multiplied by cos of 0, which is equal to 1. So this will be just 5 times 2, which is equals to 10 joules. All right. Then we look at, so we've now done force of applied. Now let's look at work done by frictional force. It's going to be, okay, so we see that it moves in this direction, right? So the displacement is to the right, but the frictional force acts to the left, which means that the angle here between them is 180 degrees. So that means that I'll have my frictional force is 1 multiplied my displacement is 2 multiplied by cos of 180, right? Cos of 180 is -1. So I'll have 1 multiplied by 2 multiplied by -1, which is going to give me -2 joules. Okay, perfect. Now we look at the work done by the normal force. Can anyone predict what the work done by the normal force and the work done by the weight is going to be? just a prediction. 0. Both of them are going to be 0 joules because we said that the formula for my work is going to be work is equals to force multiplied by delta x multiplied by cos of theta. And we can see that both my work, my displacement is that direction, my normal force acts perpendicular, and my weight acts perpendicular, right? And we know cos of 90 or cos of 270 will give you 0. And so this will always be 0. So because these two are perpendicular to the displacement, they will have no work doing. They'll be doing no work, basically. Okay, so now I can find my net force, my net work, sorry. Work net is going to be equal to my force applied, which was 10, my force of friction, which was -2, plus 0 plus 0, because my normal and my weight work was 0. So here my net work is going to be 8 joules. Friction, yes. Friction is always opposing the motion. Always, always, always. Friction always acts in the opposite direction to the motion. So if my block is moving, so this is the first way, if my block is moving to the left, friction will always move in the opposite direction, so it'll be moving to the right. Okay, so that is my work, 8 joules. Now, there's a second way that I could do it, right? And that could be by finding the net force on an object, right? So let's look at way 2. If I have an object and I said that, okay, I'm just going to draw a free body diagram or just a force diagram. So I said this is my force applied. This is my force of friction. This is my normal force. That looks like a W. This is my normal force, and this is my weight, right? We are going to find, and it's always, yes, it's always going to be opposite the direction of motion. Sorry, I missed that. We have this force diagram, and we want to find the net force acting in either the left and right direction and the up and down. So let's look at normal force is going to be, the normal force is equal to the weight, right? And the weight is equals to m times g. So these two forces cancel out. One of them is going up, so it's going to be positive. The other one is pointing down, so it's going to be negative. So I don't have, my block is not moving up or down. So it's not even gonna have work to be done in that direction. Remember we said work is equals to force times displacement times cos of theta. And we said it is imperative, it's so important that we have movement in whatever direction we want to find the work in. In the case of this moving block, it doesn't move up or down. So we don't have a displacement in the direction of, like in up or down direction. So there's no work done by the normal force and the weight, okay? So now all I have left is I have my force applied, which is 5 newtons, and I have my force of friction, which is 2 newtons. So what is my net force? What is my net force going to be? Oh, was it 2 or was it 1? I think it was 1. Sorry. Yes, it was 1. Sorry. So my net force is going to be 4 newtons. Yes. Okay, perfect. And so now I can find my network by just saying my network is equals to my, okay, so it's going to be 4 newtons to the right, right? So my net force is going to end up being like that. F of net, right? And so we say that this is equal to F net multiplied by delta X multiplied by cos of theta, right? We said that my force net is acting towards the right and my displacement is also acting towards the right. My delta X is also moving towards the right. So that means that the angle between my force and my displacement is basically zero. And so I have my force net is 4 multiplied by my X, which was 2, multiplied by cos of 0, which is equal to 1. And so, sorry, I put X there instead of 2. And so this is going to be 8 joules. Okay, so using both of these ways, you'll get the same answer, right? For what the net work is done. So you can either find each individual work, so work done by force of applied, work done by force of friction, work done by the normal force, work done by the weight, or you could find the resultant force of all of these forces acting on it, and we found it to be 4 newtons to the right, and use that in your equation to find what your work is. Which way do you guys prefer? I know which one I prefer. Which one do you guys prefer? Way 1 or way 2? Oh, wow. You're like split down the middle. I'm not allowed to choose favorites, but way, way 1. Anyway, yeah, way 1 feels a lot more doable to me because it means that I can break everything down. Like I don't have to find the resultant first and then maybe make mistakes, like look at, oh no, I don't know how to do this. I don't know how to do this. But way 2 is also favorable. Like if you know your Newton's diagrams and you know how to draw free body diagrams really well, then you shouldn't really worry that much. But you can use either way and you'll get the same answer. Okay. So now we have a very nice, I don't know why I didn't put a space between these two. I have this over here. Okay, so I'll draw the free body diagram, then we'll work on the side. I push a box 10 meters across the carpet to the right. So I have a box and I am pushing it and it moves 10 meters right to the right. Okay, so this is my delta X. Right. With an applied force of magnitude 15 newtons. So I'm pushing it, so it's coming from this side, 15 newtons. And a magnitude just means like how big the force is. And there is a frictional force of 5 newtons acting on the box. And we said frictional force acts in the direction opposite to which it's moving. We said it's moving towards the right. So that means my frictional force has to be, is it 5? No, it's not 5. My frictional force has to be 5 newtons towards the left, right? Now, remember, we said that we can be asked to calculate these things separately. We can be asked to find, like what they're saying here, what is the work done by the applied force? So you can find the work done just by the applied force. You can find the work done just by the frictional force. And then you can find the net work done by both of them. Okay, so I'm going to give you guys 2 minutes. Find me the work done by the applied force and the work done by the frictional force. And then we'll do the work done by both of them together. So I'm giving you 2 minutes to try that. What is the work done? So we're doing A and B. What is the work done by the applied force? And what is the work done by the frictional force? And then if you're fast enough, you can go ahead by a little bit and find the net work done on the box. Okay, so I'm giving you 2 minutes to try those two. You should actually be able to finish all the way to C. So yeah, let's see if you guys are good. So we're looking for the work done by the applied force, the work done by the frictional force, and if you can find the work done by the net work done. Okay. So I'll give you 1 minute. It really shouldn't take too long. We'll see how you guys do. We have 15 seconds left. Three, two, one. Okay, so let's work through this together. So we said work is equals to force multiplied by displacement multiplied by cos of theta. We said the applied force is 15 newtons, so you can say work done by the force applied is going to be 15 multiplied by the distance that it travels, which is 10, multiplied by the theta. So we said it's moving in the x direction and the force is in this direction. So it will be cos theta or cos 0. And this gives you 150 joules. Okay, then we look at the work done by frictional force, which is going to be equal to, we said frictional force is 5 multiplied by the displacement. The displacement is going to be the same each time. And cos of, so this is the direction of the displacement. This is the direction of the force, frictional force. So my cos is going to be of cos of 180 degrees. So I'll actually get minus 50 joules. And so my net work is going to be, my work net is going to be my work done by my force applied plus my work done by my frictional force, which is going to be 150 minus 50. So my net work is 100 joules. Okay, that should have been fairly nice and simple. And it looks like everyone was getting the correct answer. Well done, guys. Okay, perfect. Okay, now we look at one that's a bit like students get scared when they see an inclined plane. But Joburg is all hills. Oh, wait, I'm assuming everyone's from Joburg. But South Africa is all hills. So you need to be able to work out what happens on those hills. Okay, so I have this, right? A boy drives his 3-kilogram remote control car up a 4-meter long track inclined at 25 degrees to the horizontal. The car's motor exerts a force of magnitude 40 newtons and the magnitude of the frictional force is 15 newtons. Calculate the net work done on the car. Okay, so net work means that we have to look at all the work done by all the forces on this car. Okay, first order of business is to draw a free body diagram. Okay, so let's look at that. I'm just going to draw it as a block. Okay, so we have a force of, okay, let's just draw it. Yeah, what forces are we going to have on this block? So we know that the car is definitely experiencing gravity, so we can draw our force of gravity down there. We also know that they've told us that it undergoes friction, so we are going to have my frictional force. I'll zoom into this once we're done drawing my free body diagram. Okay, we'll have a frictional force there. Okay, and we can also look at, do they tell us that, okay, they tell us that the car's motor exerts a force of magnitude 40 newtons. So that's going to be my applied force. So force applied. And we also know that we have my normal force acting perpendicular there. Okay, so we have gravity, we have normal force, we have friction, and applied force. Okay, so this is what looks very wonky. Let's try and maybe draw it differently or more clear. Okay, so I have my incline plane, and they told us that my incline is 25 degrees. I have my, I'm going to break down my two gravity forces. So that's going to be my normal force. I'm going to change this into FG perpendicular and FG parallel. And then I've got my frictional force as well, so force of friction. And I also have my applied force, which is the force applied. So we've got quite a few forces that are acting on this object. And of course, this is going to be moving up this hill. And they said that this hill is how many meters? 4 meters long. And the mass of the car is 3 kilograms. Okay, so we are going to find the network. We're trying to find the network on this car. So we said we're going to use way 1 here. And we're going to say, okay, the network looks at all the forces that are acting on this and looking at what work they do, and then we're just going to add them together. So network is going to be equal to work done by the force applied. I'm sorry, let's make that work. Work done by the force applied plus work done by the frictional force plus work done by the normal force plus work done by the force of gravity in the perpendicular direction plus work done by the force of gravity in the parallel direction. Okay, so those are all the works that I have to work with. Okay, so first let's do, okay, we're going to look 1, 2, 3, 4, 5. Okay, so first let's look at work done by the force applied. So we're just going to work them one by one. So work done by the force applied is going to be equal to force. We know, okay, I'm just going to write work equals force times delta x times cos of theta so that we don't have to keep doing that. So they're saying that the force applied acts in that direction. And so do you agree that it's working in the same direction as my delta x? My delta x is there and my force applied is acting in the same direction. So my cos should be 0. So I'll get then my force applied, we said was, this was 14 newtons. This was 5 newtons. Let me just check. 15 newtons. 15 newtons. Okay, so my force work done by my force applied is going to be 40 multiplied by my displacement, which is 4 multiplied by cos of 0. So I get this work to be 40 multiplied by 4, which is 160. 160 joules. Perfect. So now we have my work done by my force applied done. Okay, now let's look at work done by frictional force. That gives us, so we know that frictional force is acting in this direction, but my car is moving up there. So the angle there is going to be 180 degrees. So we're going to have work done by frictional force is going to be 15 multiplied by delta x is the same, multiplied by my cos of 180 degrees. And so this is going to be 15 multiplied by 4 multiplied by -1 gives me -60 joules. Okay. Then we also have, now we're going to look at my work done by, let me just move this down. Okay. Now we have work done, so we've done work done by friction force. Work done by normal force is going to be what? What is the work done by my normal force? We're on an incline, but I can see that my delta x is this way, and my normal force is always perpendicular to the slope. So this one is going to be 0, right? Because we know cos of 90 is 0, so this is going to end up being just a 0 work. Okay, so now we have a work done by that. Work done by FG perpendicular. First of all, I'm just going to split this into two. FG perpendicular and FG parallel always have the same formulas. So you always see them have FG perpendicular is always going to be M times G times cos of theta. So whatever the incline is, so in this case it's 25, and FG parallel is always going to be M times G times sine of theta, right? And so here my MG parallel, or my FG parallel, sorry, or perpendicular is going to be mass, which was 3 multiplied by 9.8 multiplied by cos of 25. And this one is going to be mass times 9.8 multiplied by sine of 25. What is my FG parallel and what is my FG perpendicular? What does that give you? FG perpendicular should give you 26.65 newtons, and my FG parallel should give you 12.2, oh sorry, 12.42. Okay, so now I can use these to find my, we were doing this just so we can find our work done by those two. I'm just going to say 4. Work done by my force of gravity perpendicular is going to be 2.6. So 26.65 multiplied by delta x, which is 4, multiplied by cos of what? What is the angle between the displacement and FG perpendicular? 90, which means this is going to be cos 90, which means this is 0. So my work done by my FG perpendicular is going to be 0, right? And then finally, my work done by my FG parallel is going to be equal to 12.42 multiplied by 4 multiplied by cos of, in which direction is it moving? It's moving opposite, right? So we're going to have equals to cos of 180. This is going to give me 12.42 multiplied by 4 multiplied by -1, which gives me minus 49.68 joules. Okay, so now let's see what I need to combine. Okay, I find my work done by my force applied. I've found my work done by my frictional force. I found my work done by my normal force. I found my work done by my force perpendicular, and I found my work done by my parallel component. Okay, so now I just need to add them all up. So we'll say work net is equal to 160, which is here, minus 60, which is here, plus 0, which is this, plus 0, which is this, minus 49.68, which is this. What do you guys get when you sum all of these up together? Perfect. So my work net is 50,32 joules. Okay. So we first started by saying, okay, what does my free body diagram look like so that I have all of my forces? I looked at my free body diagram and I said, okay, those are the forces on my object. Then we break apart all the different works that we have. We have work done by force applied, work done by frictional force, work done by normal, work done by force perpendicular, and work done by FG parallel. Then we calculated the forces of everything. And to find my FG perpendicular and my FG parallel, we used our known formulas, which will always be true. And so then after we found all of those works, we could sum them up to get me that. Okay, so this is a typical exam question where we'll give you something on a slope and ask you for the net work on that object. Okay, so that is my net work. So you round off to 2 decimal places. So you're going to round off to 2 decimal places as you're working. So yeah. Okay. Then we look at the work energy theorem, right? And the work energy theorem basically finds a way to relate the work done by an object to its kinetic energy. So this whole time we've been looking at what happens when I push something, what happens when a car is moving up a slope, what happens when certain things are happening and energy is transferred from one form to another, right? And so they found that you can actually find the net work, or you can associate the net work done on an object by a net force as being equal to the change in that object's kinetic energy, right? And we know kinetic energy to be 1 over 2 mv squared, where m is my mass and v is my velocity. So this is mass in grams and velocity in meters per second. And so from there, we can say that work net is going to be equal to half mv final squared minus half mv initial squared. And this will help you find what the net work on an object is. But remember, we said also net work is equal to force, or the net force, multiplied by the displacement, multiplied by cos of theta. So that will also equal to half mv final squared minus half mv initial squared. And so we can actually find certain components. So sometimes they'll give you the change in kinetic energy, they'll give you final velocity and initial velocity, but they won't tell you what is the net force on the object. And they'll ask you, what is the net force on that object actually? And you can use the work energy theorem to find what the net force on that object is going to be. Or they can give you the net force, but ask you how far did the object move? And so you can use this formula again to find what the displacement is by just moving everything else to the other side. Okay, so this is basically the work energy theorem. They'll give you this formula in your formula sheet, but you need to know how to be able to convert it to then this, which is more useful than this one. Okay. Yes, so it depends on what your teacher has suggested. So if your teacher suggested that you should round off to 3 decimal places when you're working, then rather do that. Some teachers have a varying as to what you should keep, but yeah, rather go with your teacher's advice and stick to that. If they say that you should work with 3 decimal places during your calculation, then work with 3 decimal places until your final answer. Okay. But that is usually the recommended one, Elisa, because it means that you won't lose any like very big significant information when you're rounding. Okay. So here, this is how a typical exam question could look. So they could ask you, the net force acting on a 2 kilogram ball is 5 newtons to the right, right? the force or the ball moves 10 meters to the right. If the ball starts from rest, use the work energy theorem to calculate the ball's final velocity. So first thing that should be happening when you see this kind of question in your exam is, okay, what formula am I going to use? Oh no, actually, before that even, let's draw a free body diagram, right? So they said we have a ball, right? And it's rolling, and the net force on the ball is 50 newtons, right? So that's F net acting on the ball. And the ball moves 10 meters to the right. So from there to there, delta X is 10 meters. If the ball starts from rest, what does starts from rest mean? What does that term mean? That starts from rest. It means that V initial, so the initial velocity is equals to 0. So it means that it will have a certain velocity, right, which we don't know yet, which I think they're actually asking for. Yes, they're asking for the final velocity of the ball. So, and they said use work energy theorem, okay? I'm forced to use work energy theorem. If they tell you to use work energy, you have to use it. If they don't tell you that, then you can use whatever else you can figure out, but you always, they tell you to use work energy, you're going to use that. Okay, so now I know that my work energy theorem says work net is equals to my change in kinetic energy, right? And we said in the previous slide, we know that net work is equals to the force net multiplied by the displacement multiplied by cos of theta is going to be equal to a half the mass times velocity final squared minus a half minus the mass velocity initial squared. Okay, so we said we're looking for the final velocity, which is over here. That's what our aim is. So let's see what we can substitute in so far. What is my force net? It's 50 newtons. So 50 multiplied by my delta x, they told me, is 10, multiplied by my cos theta. My force is being applied in towards the right. They've told me there, told me here, and they told me that my ball moves towards the right as well. So delta x and force net are acting in the same direction. That means that my cos is going to be, my theta is going to be equal to 0, is equals to a half m. Oh, we know the mass of it. We know the mass is 2 kilograms. And velocity final squared, we're looking for the velocity final, minus a half, mass is 2 kilograms, velocity initial is 0 squared. So this whole term over here kind of goes away because that's equal to 0. Okay, so now let's look at this side. Oh, I should have made this as 0. The left-hand side of my equation is 50 multiplied by 10 multiplied by 1, which means that this is equal to 500, is equals to a half times VF squared. These two cancels out, so we have V final squared. And so to find V final, I have to square root both sides. So I get my V final is equals to square root of 500, and that is equal to 2.36 meters per second, right? And they asked for velocity, and we know velocity is a vector, so we have to say which way it's moving in, so it's going to be to the right. If they said speed, then we could have just left it at 22.36 meters per second, but because they asked for velocity, we have to say 22.36 meters per second to the right. Okay, so that wasn't bad. That was okay. Let's see if we can try another example. Okay. Now this one says, let's maybe make some more space here. We'll draw underneath that. This one says, there's a car of mass 640 kilograms, right? So now we know that mass is 640 kilograms, and it's traveling at 30 meters per second. So we know that velocity initial, I think, will be 30 meters per second. It then accelerates in a straight line down the road, right? So it accelerates. So it has an acceleration. I don't know what that acceleration is yet. And it says that the engine exerts an average force forward of 12 newtons. So 12,000 newtons is the force applied by the engine, right? And the car experiences an average frictional force of 3 newtons, 3,000, sorry, 3,000 newtons. So force of friction is 3,000 newtons. They say using the work energy theorem, calculate the speed of the racing car after it has traveled 30 meters. So essentially my delta x is equals to 30 meters. Okay. Apologies, but when do we use the work energy theorem instead of the work formula? So whenever they explicitly tell you to use the work energy theorem, then use the work energy theorem. Don't use anything else. But when you see that they're asking for velocities and speeds, and like you kind of can then gauge, okay, I need to use work energy formula because that has elements that have velocity and speed, and so you can calculate whatever they need you to calculate. Okay, the work formula is incorporated in the work energy formula, so you have to use the work formula in the work energy formula. You use the work formula like work net when you're calculating the net work on your object. Okay, so now first and foremost, always draw your free body diagram. So this one's also relatively simple. I have my car, right? It has a mass of that. It's traveling initially at V initial equals 30 meters per second. And it travels for 30 meters. And we don't know what V final is. We know that there's a force of friction acting on it, which is 3,000 newtons. And they also said that the engine is pulling it at 12,000 newtons. So this is the force applied. This is the force of friction. Looks like we don't actually need the acceleration at all. We don't really use it. They just tell you that it accelerates so that you know that the velocity changes from this initial to this final. Okay, so we've got a bunch of stuff that we have. Okay, so first of all is we can either find work net by looking at the force applied and the force of friction, or we can find the F net, then use that to find the work net. Okay, so since the previous example we used the work net, I'm going to use this way so that if you're more comfortable with this one, you also get some practice with it. Okay, so this is what our our kind of question looks like at the moment. I'm going to first find the force, the net force on it, so that I can use it in my equation that says that my work net is equals to change in EK, kinetic energy. So this is force net delta X cos of theta is equals to 1/2 mv final squared minus 1/2 mv initial squared. Okay. For an inclined object, is it possible that we calculate the net force, then our work energy equation, substitute theta equals 0? Yes, you can. You can definitely do that, Paul. Yeah, so you can choose whichever feels the most comfortable, calculating them each separately or finding the net. And if the net is up the incline, then your theta is going to be 0. Okay, so now if I look at my forces on my object, sorry, I'll have a force of 12,000 newtons here, and I have a force of 3,000 newtons here. There's normal force and there's weight, but those two cancel each other out. So my F net is 3,000. my F net ends up becoming, what is my F net? What is my net force acting on the car? Would be 9,000 newtons. Right, and it will be towards the right. Okay, it's 9,000 newtons to the right. And so now I can substitute it into my equation here. So I can say now F net, which is 9,000, is multiplied by delta x, which is 30, multiplied by cos of theta, cos of, we see that my force, my net force is acting in the same direction as my displacement. And so that means that I'll have a cos of 0 degrees. Okay, then I'll have half my mass, which is 640. And I'll have my V final, which is what I'm looking for, squared, minus a half 640 multiplied by my V initial, which was 30 meters per second squared. Okay, and so now I can put all of these things into my calculator. And when I say 9,000 times 30 times cos of 0, I get 270,000 is equals to, if I do half times 640, I get 320. V final squared minus a half times 640 times 30 squared gives me 288,000, right? And so now I can move this 288 to the other side. So I'll have 270,000 plus 288,000, and that'll all be divided by 320 equals V final squared, or let me just square root. And then to get that, I'll have to square root this side, square root this side, and I end up getting my V final as being what V final are you guys getting? 41.76 meters per second, -1. Let me just check my calculations. So the square root of 270,000 plus 288,000 over 320. Yeah, I get 41.7.46, sorry. Is it 76? Oh, sorry, I put the wrong value at the top there. 288. Yes, 41.76 meters per second. Okay, Paul, oh no, not Paul, sorry. Kotso, do you see where you maybe went wrong? Or are you a little bit confused? Okay, you ended up fixing it. Okay, perfect. Okay, cool. So this was work energy theorem when you're not given the net force, but rather you're given speeds and you kind of expected to know how to find your work from them. Or not your network, but like find. Okay. Ria, we have found that our net force is 9,000 to the right, right? And my box is moving, my car is moving to the right as well. So they're moving in the same direction. So we'll have cos of 0. The angle between two things that are moving in the same direction is 0. So we found our net force here to be 9,000 newtons to the right. Yes. So we would have chosen this way to be positive, but it doesn't matter because we always put in a positive force here and a positive displacement. We never put in, this doesn't depend on the direction. My cos is the one that decides whether my work is positive or negative. Okay. Then we have another formula that you get to use. And this one just needs you to know what the difference between a conservative force is and a non-conservative force. Now, a conservative force is one where the force or the total work that it does doesn't depend on the path that it takes. Now, this can be a little bit confusing, especially when you like, what does that mean? It doesn't depend on the path that it takes. Okay, if I have a ball on a building, right, and I drop it, right, the force of gravity is going to be working downwards, right? And if I have a ball that I'm throwing upwards, my force of gravity is still going to be working downwards, right? The path that this ball takes, whether it like, let's say there's like steps that this ball falls through. It can fall down there, there, right? And move 5 meters to go down. Doesn't matter what the path this ball took, whether it fell straight down or it fell downstairs, my displacement at the end of the day is still from there to there, 5 meters, right? From there to there, 5 meters. And typically your conservative forces will be your gravity. So you can just like learn this if it's still a bit confusing. You just know gravity is a conservative force. Elastic force is a conservative force, and electrostatics forces. Static forces are conservative forces, right? So they don't necessarily, we say they don't take away energy from the object when the path is changed, right? So if I change the path, if I make the path longer, so here with my ball that's bouncing, my energy doesn't decrease, or like it doesn't get like the energy that is removed from the system isn't decreased with a longer path. Like the same amount of energy is decreased when I'm moving from top to bottom. A conservative force, however, like friction, if I have a long path, right? Let's say I have a block and it's moving that way. If I have a short path, my friction is only going to take away like a certain amount of energy. Versus if I extend that path, if I make it twice as long, friction is going to take away even more energy. So like the longer my path, so it depends on my path. The longer my path, the more friction is going to remove energy from my my system, right? And so examples of non-conservative forces are friction, air resistance, applied force, and tension. So these are the forces that would be considered as non-conservative forces. Okay, so if you can just memorize, okay, these are the most common ones. Gravity plus elastic and electrostatic are your conservative forces. And then everything else, friction, air resistance, applied force, tension, These are all non-conservative forces. Okay. Ria, the way that I calculated the net force is I said that there's a force acting towards the right, that's 12,000 newtons, and there's a force acting towards the left, that's 3,000 newtons. So I said 12,000 minus 3,000, which gave me 9,000 newtons. That's how I found my F net. Okay, so we can use this information that we have on conservative and non-conservative forces to calculate work, or like when you have something that's maybe missing and you want to find okay, so let's break down first, then we'll see what we can find from using this. So this formula is also on your formula sheet, and you'll see that we said NC stands for non-conservative, right? And this is your applied force, your tension, your frictional force. Those are all your non-conservative forces. So the work done by those, again, we can sum it down to just being your network, or your F net of all these forces combined is delta X multiplied by cos theta is equals to the change in kinetic energy, which we had in our previous equation, which was half mv final squared minus a half mv initial squared, plus potential energy. Now, potential energy is just the mass times the gravitational force multiplied by the height. So how high above a certain reference point it is. So your height final minus mass times gravity times height initial, right? And so this is what our equation can be expanded to. So sometimes they'll say, what is the height that it's dropped, or something like that. Or they can also ask you, what is the final velocity, after they've given you like a bunch of stuff. So you know that if you're working with something that's falling or going from a certain height to another, and they're asking you for like velocities, then you can use this equation that says that the work done by non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. And remember, we can also find this by saying work done by force applied plus work done by friction plus work done by tension, if we have tension. So these are the two ways that you could find that work done by non-conservative forces. Okay, so let's see if we can do a nice example. Okay, I fear that we may not finish, so I'm just going to go through power. Power is super simple. It's again work over delta time, so they'll usually give you the work done by a certain system over a specific time, or the force multiplied by the velocity. Okay, so this is power. You'll find it on your formula sheet. Okay, so now here, I want us to try this example. So I have a 70-kilogram skateboarder, right? So somebody who's on a skateboard and he skates down a slope while experiencing a frictional force of 119 newtons. The slope forms an angle of 30 degrees with the horizontal 30 degrees, and the skateboarder converts a distance of 10 meters. So the distance that he travels from there to the bottom is 10 meters. The speed of the skateboarder at A, so this is A, is 6 meters per second. Calculate the gravitational potential energy of the skateboarder at A. Now, this we haven't really covered, but you guys should know. How do you find the gravitational potential energy of the skateboarder at point A? What would that be? So I'm looking for EP at point A. What is that going to give me? They tell us a height. Oh no, they don't tell us a height, but we can find it out. we know that we have a triangle. We have this being 30 degrees and this being 10 meters. So we can find out what this is. We can use trig to find out what that other side is. And the trig would be basically sine 30 is equals to, sometimes canceling O over H. So I can find my opposite side by saying 10, which is H, multiplied by sine 30 is equals to my opposite. You should get an opposite of, so our height equals 5 meters. Okay, so I'm looking for my gravitational potential energy. What is that going to be equal to as a final answer in joules? What is my gravitational potential energy going to be? So I know the equation is going to be mgh, or m times g times h. So what is my gravitational potential energy? Perfect. So I know my mass is 70 kilograms. I know gravity is 9.8. And I know that my height, now that we've calculated it, is 5 when it's above the ground. So this is 0, this is 5. And so my answer would be 3,430 joules. Right. Then they say, what is the speed of the skateboarder at B? Okay, so now we want to find the speed, but before we can do that, we have to find, okay, we're going to use this equation that we've just learned, and that equation says that the work done by non-conservative forces is going to be equal to the change in kinetic energy plus the change in potential energy. Okay, so let's look at all the forces that are acting on my object, right? So I have this skateboarder and he is moving on an incline. So I'm just going to draw it on the dashed line, right? He's going to have FG perpendicular, boom, FG perpendicular. He's going to have FG parallel. He's going to have a normal force, and he's going to have an applied force that's in the same. Does he have an applied force? No, he doesn't have an applied force. So basically his gravity is pulling him down. So this is the applied force. And then we have a frictional force of 190 newtons. Okay, so in this case, my non-conservative forces are my force of gravity, because that is essentially my force applied. That's what's getting him to move forward. And my, we said gravity is a conservative force. That's not going to work. Normal doesn't really depend on my path, so that's also going to be it's not going to be included. But even if it was, this would equal to 0 because there's a 90 degree there. And so we can say that this is going to be my force and my force of friction. So my FG parallel and my FG that. Okay. Now I'm going to say that, okay, I'm going to say, okay, I'm going to split this work into 2. Should I? Or should I just do net force? I think net force is simple enough. We have FG parallel. We said FG parallel is always going to be equal to mg sine theta. And we have our frictional force, which we're given is 190. What is mg sine theta equal to? We know it's 70 kilograms multiplied by 9.8 multiplied by sine of my angle was 30. What is my force of gravity parallel? 70 multiplied by 9.8 multiplied by sine 30. So let's just zoom out so that you can see the whole question. Okay, and so that gives my FG parallel to be 343 newtons. Okay, so now I have 343 and 190 newtons. So that means my F net is going to be down. My F net is going to be, what is my F net going to be? Perfect. It's going to be 153 newtons. So that's my net force that's acting downwards. Okay, so now we can say my F net multiplied by my displacement multiplied by my cos theta is going to be equal to 1 over 2 mv final squared minus 1 over 2 mv initial squared plus mgh final minus mgh initial. Okay, so now we can start populating our equation or filling in our equation. I'm just going to write it a bit bigger going on to here. We said my F net is 153 newtons. So I have 153 multiplied by my delta X was 10 meters, right? So that he moves down 10 meters multiplied by my cos theta. I know my F net is acting in the same direction as in which the displacement is. So it's going to be cos of 0 is equals to 1 over 2. Mass is 70. V final, we don't know what that is. That's what we're looking for. Minus 1 over 2, 70. V initial, do they tell us the initial velocity? The speed at A is 6 meters per second, so 6 meters per second. Let me try and get this to them. Did it work? No, it didn't work. Let's bring it back. Okay, I'll just move down a little bit. Okay, so this was our kinetic force plus I'm going to have mass is 70, 9.8. The height final is 0, right? Because when he's here at B, I've reached 0 in terms of my distance from the base. And then that's going to be minus mass, which is 70 multiplied by 9.8. Height initial was 5, which we calculated before. Okay, just going to zoom in here. Then I have, okay, so now I can calculate what each of my sides is going to equal to. I have my 153 multiplied by 10 multiplied by cos theta is going to give me is it 1530 is equals to, I'm going to have here 35. Oh no, let's move it down a little bit. One five three zero is equals to 35 B final squared minus 1260 plus Oh no, not plus, it's going to be minus because we have a minus there. Have minus 3, 4, 3, 0. I think we did something. Yeah. Oh no, sorry. This was incorrect over here. So we weren't supposed to include our gravity as our force because we said gravity is a conservative force. So the only force we should be looking at is my frictional force. That simplifies things a lot more. Sorry about that. So we have 190 is now our force net because that's the only force we're going to be considering, multiplied by 10, multiplied by cos of, we said my skateboard is moving that way, my frictional force is moving that way. So that is 180. So it's cos of 180 is equals to, it's going to still be 35. Everything else on the right-hand side was fine. Minus squared minus 4690. Sorry about that, guys. So here we should get minus 1900 is equals to 35 velocity final squared minus 4690. And so I should get 2790 is equals to 35 multiplied by velocity squared. And then if I divide both sides by 35, I should get 9,71 4 is equals to V final squared. And so my V final is 8,93 meters per second. Okay, so it almost caught me there as well. So the only force that is non-conservative in this case is my frictional force. So my force of gravity, both of them don't work, and my normal force also don't add any, can't be included in this formula over here. Okay, so this would be how we would calculate that over there. Are we only considering one angle on the left side while we have two forces? What are the two forces that you're referring to? Oh yes, we have a direction as well. So it's going to be, we can say, what do they say here? Down the slope or to the right? Down the slope or to the right, because by the time he gets here, he'll be moving that way. So you can say right. So here we weren't told, we weren't given any applied force. We were just told that he's skating down the slope and he has friction, but we don't have an applied force. So he's not, nothing is pushing him forward. So he wouldn't have an applied force. If there was an applied force, then we could include it in this equation here. Okay. So let's say, no, we couldn't have done that. Okay, yeah. The last one was this question with power. So it says a car with mass of 500 kilogram accelerates from 10 meters per second to 50 meters per second in 25 seconds on a horizontal frictionless surface. Calculate the car's power. All right. So we said power is equal to work over change in time, right? And we know that work is equal to force multiplied by delta x multiplied by cos of theta, right? So we first need to find what is the force, because we don't know what the force is. We know that there's a car, right? And it's accelerating. it has a V initial, it has a V final. V initial is 10 meters per second, V final is 50 meters per second, and it does that in 25 seconds. So we can find the force by saying we know force is equals to mass multiplied by acceleration, right? So this is just one of Newton's laws, right? And then we can then say, or we could have said work net is equals to the change in kinetic energy. Okay, right? We know that kinetic energy is 1 over 2 mv final squared minus 1 over 2 mv initial squared. So we know that this is equal to 1 over 2 m is 500, v final squared is 50 squared, minus 1 over 2 mass is 500, multiplied by v initial squared 20, oh, what was it, 10 squared. This should give you a work of, I did it this way, let me just check that it gives you the same answer. So 1 over 2 multiplied by 500 multiplied by 50 squared minus 1 over 2 multiplied by 500 multiplied by 10 squared. That should give you 600,000 joules. Right, so now you have the work. We looked at this equation before in one of our examples. So now we can say that power is equals to 600.23 over the time that it took, which is 25 seconds. So my power is going to be 24,000 watts. You also could have used, I remember somebody asked about the equations of motion, very beginning. You could have used the equations of motion to find this initial, to find this acceleration. So these are two ways, they'll give you the exact same answer. You find force by mass times acceleration, because you have the initial velocity, you have the final velocity, and you have the time. And you can also find it using just the work net is equals to the change in kinetic energy, and in that way. Okay. That is most, if not all, that we cover in work energy theorem. If anyone has any questions, you are welcome to leave them in the chat and I'll answer them. So I'll stay on here for just another 5 minutes if anybody needs any more clarification. But that's it. Well done, guys. Remember to do practice still beyond this on past papers and try to get yourself familiar with drawing diagrams, knowing how to find the net forces, knowing how to apply each equation, to know when to use the work energy theorem, when to use the conservative force equation, when to do that. So the recordings for this lesson are going to be published on the Learning Space YouTube channel. So if you can just there'll be a link in the chat for all the links. So for TikTok, for Instagram, for YouTube, all of those there. You can also leave a review on Google. So if you go on Google and you type in the Learning Space, you'll see us there with our logo. And so you can review and say, this session was really great. Let's do more. Or something like that. Or just like how you felt about the session, what you feel like helped really, or what you enjoyed about it. Yeah, so you can leave them there. And yeah.